Meeting of Greyhound. Thanks to everyone for coming out on such short notice, and a big thanks to our speaker on presenting on such short notice. We're lucky enough to have Justin Werfel, who's going to be talking about artificial swarms and collective construction. He's currently working at NEXI as well as the Harvard Medical School, and we're extremely happy to have him present here. So without any further ado, here's Justin. Thanks very much.
So my skills are in dropping things. Well, tell me if you can hear this, or wait if you can't. My broad research interests are in understanding and designing emergent systems. That is, systems of many simple interactive components where you may be able to understand the components very thoroughly in isolation. But when you get many of them together, some interesting new behavior emerges from their collective actions.
And the breakdown paparazzi.
Some interesting high-level behavior that you might not have been able to predict from studying components in isolation emerges. So I've worked on a number of systems sort of under that heading. The one that I'm going to be talking about today is the first one, swarm robotics applied to collective construction. So these systems are inspired by social insects, which have just remarkable abilities to build things. This is a termite mound. These things can be built 10 meters high. They extend for meters below the ground. They're full of all kinds of complicated functional architecture, and the whole thing is built by vast numbers of tiny, simple insects, all acting independently with no sort of central control or supervision. So it's a fascinating question to ask, how is it that these insects can build these structures? I've actually taken the opposite approach and asked, how could we harness that power? If you had an artificial termite colony, how would you program it so that it would build you something that you want? So the ultimate goal here, in sort of a practical sense, is to be able one day to take a bucket of robots, give them a supply of building material and just a picture of something you want them to build, and be able to walk away and know that they will build you that thing. But before we spend a lot of time doing this, it's worth asking if it's worth doing. And after all, we have a perfectly good way right now of performing construction. The fact is that construction is pretty much the one big human production activity that has largely avoided automation so far. And there are ways we could stand to benefit from it. Some of the problems reported with traditional construction include things like high accident rates, low efficiency, high cost, labor shortages, the sorts of things that automation traditionally helps with. And actually, just about a year ago, Korea announced a major new initiative to introduce automation into construction. The goal is eventually to have a completely automated system. Their reported reasons for doing this are exactly these kinds of things: to reduce costs, boost productivity, lower accident rates, reduce labor shortages, and they're putting 16 billion, monetary units into the project. So I think there's room for an impact here. I think there's actually even more promise for introducing automation in settings where we don't already have a way of doing it. So, for instance, in outer space, if we want to send astronauts to other planets, it would be great to be able to send a team of robots on there first to build them a place to live. Or closer to home, there are underwater applications, from oil drilling platforms to marine research stations. And these are places where it's difficult or dangerous for people to go and do the work themselves. So one approach you could take to try and introduce automation into construction would be to use one or a small number of very complicated robots. These would have the advantage of being individually more capable. But if you can do things with a swarm of simple robots, that sort of approach can have a number of strong advantages. So for instance, if you can break the system down, break the overall task down into a large number of independent subtasks, then different robots can be working on different tasks at the same time, you can get large overall speed up. Swarm systems tend to be robust to the loss of individual components, so when there's one robot or many robots, it doesn't necessarily have much of an effect on the overall system. And simpler robots, with simpler robots, there's less to go wrong with any one of them. But the same things that make a swarm potentially very powerful, also make it very difficult to work with. So you've got lots of things going on all over the place at the same time, but no kind of central supervision to make sure that everything's happening on task. And there may be robots leaving the system, robots being added, they may be acting in some unpredictable order. Simple robots are not going to be capable of very much. They're going to be limited to knowledge about maybe just their local surroundings. And the biggest issue here is that this is a case of trying to design an working system. It's hard enough to predict by looking at a set of low-level rules what a set of agents following those rules is going to end up producing. In general, the best we may be able to do is to simulate and see what ends up happening. And here we're actually, we're looking for something much worse. We're demanding a particular final result and saying we have to find a set of rules that's going to produce that result. And that's what I'm going to describe doing. So the result is going to be an ability to give a simple set of rules and a high-level description of what you want to arbitrary number of robots. And then they just sort of go out, and without further intervention from you, they'll take appropriate actions as necessary and wind up building the thing you ask for every time they do it. So the way okay, before I actually talk about how that's done, let me say a few things about some related research. Most of the work in what you might think of as artificial collective construction focuses on other aspects of the problem. So whether that's on hardware design, or on clearing a workspace of debris, or adding communication to the system to improve its performance. And as a rule, these other studies either don't have the goal of producing a particular desired structure, or if they do have that goal, then the user has to provide a particular sequence of block attachment events that has to take place in order to build the structure. And that's what I want to automate and parallelize. There's a number of other research areas that are closely related enough to this to be worth mentioning. Let me just very quickly go over a few of them. So there's sort of insect-inspired studies that look at the forward problem, looking at a low-level set of rules and trying to conclude something about the system that is going to wind up producing. Some people take an evolutionary approach, trying to automatically generate rules that will produce a particular desired structure. In robotics, there's work in formation control of mobile robots and in modular self-reconfigurable robots, where the idea is to have a large number of identical units, all of which are mobile, subject to some set of movement constraints that need to rearrange themselves into some desired structure. The area that's probably closest in spirit to what I'm describing is program self-assembly. This is the problem trying to design a set of tiles whose edges have certain binding properties, such that when you put them all together in a box and shake them up, they wind up assembling themselves into the structure you're looking for. And one thing about a lot of these studies is they don't tend to take into account the physical movement of the tiles. And as a result, the structures that are formed tend to be subject to sort of crystalline defects. Holes in places where you don't want them, but tiles that come together in sort of inappropriate order and block off an area that now other tiles can't get to. And the approach that I'll describe is centrally designed to avoid that problem. So what I want to do with this talk is to spend most of it sort of going through a fairly simple case study where I'll talk about the process of algorithm design for a system that can build arbitrary solid structures in 2 dimensions. One of the tools that I'll be talking about to do that is what I'm calling extended stig merging, which, in very brief, is about trying to improve the system not by improving the capabilities of the robots, but instead by improving the capabilities of the environment, in this case, the building material. So then I'll show some movies of robots that instantiate that first system, and then talk about extensions to more arguably relevant structures. So there are 3 kinds of elements in the environment. There's going to be mobile robots, there are movable building blocks, and there's a marker that indicates where you want construction to take place. And the idea is to deploy all of these things in an otherwise obstacle-free workspace, and have robots collect blocks and build the structure you're looking for, starting at the marker. I'm going to assume that robots are able to move in any direction in 2 dimensions, and not bump into each other. They can fetch blocks and bring them to the structure. Once they've done that, they can follow the perimeter of the structure, carrying the block. And once they have found a place where they want to attach a block, they're able to attach it. One thing I'm not assuming is that robots are going to explicitly communicate with one another. So there are ways you can think about adding communication to the system to improve its performance. But there are reasons that it's nice to not have to rely on a communication system in order for the system to function. To start with, mobile web wireless networking is a major open research area. So the only communication that I'm going to that's going to take place between the robots in this system is implicit, through the manipulation of a shared environment. Now, if you're talking about construction, odds are you're going to want very precise alignment of building blocks. But you want a very solid looking wall. But manipulation of the physical world is a notoriously difficult thing for mobile robots to do, particularly very simple ones. And so I'm going to require that blocks be equipped with some kind of self-aligned connectors, in the spirit of making things easier by improving the building material rather than the robots. As for the physical movement of the blocks, as you mentioned is a major consideration, I'm going to make the following conservative assumption, that in the middle of a wall like this, there's plenty of room to add a block anywhere there. And similarly, a site like this, there's plenty of room for a robot to maneuver a block into place. But I'm going to say a site like this is too physically constrained to require that a robot be able to deal with it. Whether it's to shove it into place or to apply mortar around the edges or whatever needs to be done to attach it from that site. And similarly, a site like this one, I don't want robots to have to be able to deal with that. And the nice thing is that by preventing sites like this, situations like this from ever occurring, that's also going to eliminate more complicated situations, like where a robot might have to maneuver a block down a long tunnel or around corners, or where a site gets completely closed off and inaccessible. So the general idea is going to be for robots to go get a block and bring it to the structure, and then walk around the perimeter until they find a place where they want to attach a block, and then attach it. And where they want to attach a block, that's the heart of the problem. That can be broken down into a couple of somewhat independent sub-issues. So first, you want to be able to tell the difference between a site that should eventually be occupied versus one that should be left empty forever. And if you can attach blocks at all of the former and the end of the latter, then you've built the structure you're looking for. But you also want to be careful about when you attach blocks there. There's the question, do I ever want to attach a block here? And there's the question, do I want to attach a block here now? There needs to be some kind of partial ordering on when you attach blocks based on where others already exist, because otherwise you might end up with these dead-end states where you still want to attach more blocks, but now you can't physically get to some of the sites you need to get to. And then whatever you end up doing, it better work with the swarm. In particular, you don't want separate robots to be able to take mutually conflicting actions. So let's talk about this one at a time. How can you tell the difference between a site that should be occupied versus one that should be left empty? Well, I've said that I want you to be able to give the system a high-level representation of what you want in a picture. It's called the shape map, and that could be as simple as an occupancy grid that specifies in some coordinate system which sites are to be left occupied, which are to be left empty, which are to be occupied. So if robots all have a copy of the shape map, and if they're able to figure out their location in a common coordinate system, which in general is a very difficult thing for mobile robots to do. If they could do that, then this first part of the problem is done. And having access to the shape map and knowing where you are, you can just look up on the shape map and see whether the site is supposed to be occupied. The second issue about avoiding unfillable gaps, it turns out to be necessary and sufficient to require that robots never attach two separated blocks in the same row or column if all of the sites between them are also supposed to be occupied. Because if you ever get into one of these situations, then at some point as you add additional blocks, you end up with one of these unfillable gaps. So it turns out that if you can do these things, that is, figure out your position in a common coordinate system, and then attach blocks anywhere they're supposed to go, as long as you never inappropriately attach separated blocks in the same row. That will provably lead to the construction of any structure that you ask for from the following class. First, it should be solid. This approach isn't guaranteed to work on structures that enclose internal space. I'll say why in a moment. And second, because the approach depends on perimeter following, any alleys that you want to leave in your structure had better be wide enough to let that take place. Okay, so I've said that if you can do this stuff, you get whatever you're looking for, and let me give you a sense of how to prove that that's true. So the first thing you want to show is that you're not going to end up with unfillable gaps. And the key there is that the only way to get an unfillable gap is to attach two separated blocks in the same row, which we're saying robots are not going to do by hypothesis. The more subtle thing is to show that you're not going to get deadlock situations, where you still want to attach more blocks, and you could attach more blocks, but you're just by statute forbidden from doing so because of this rule. And so you can show that that won't happen by contradiction. Let's suppose then you're in a deadlock state. That is, for every site where you want to attach a block, there exists some other block already present in the same row that's preventing you from doing so because all of the sites in between are supposed to be occupied. So if you can attach a block here, that means there's something to attach it to. Because the structure is being built contiguously from a single initiation point, these two existing blocks must be connected by some chain of existing blocks. I'll draw that like this. Okay, so the idea here is there are some blocks that come up this way. There are supposed to be blocks here. So we've got a loop, right? And this is where it's important that the structure you ask for is solid. So the only way that this loop structure could be a legal thing to ask for is if the whole thing is supposed to be filled in. If the whole structure is supposed to be solid. So in particular, these sites are supposed to be occupied. But now, because these two blocks are already present, this would be a case of separated blocks in the same row inappropriately, sort of contrary to the assumption that we've been building the structure in an allowed way so far, unless all of these sites are already occupied. So now look at this site. We're almost done. This one is it's a site where there is no block, and there's supposed to be one, and there's no way that adding a block here can cause problems. So this is a contradiction. There is a place where you can attach a block, and this wasn't a deadlock after all. So now the question is, how do we do these things? Okay, so first, how can robots figure out where they are in a shared coordinate system? So here we're going to use a tool that social insects use to coordinate their behavior. The term is stigmergy. I imagine a lot of you are familiar with it. The idea is that it refers to storing information in the environment for later use by the same array agents. So the most famous example of this is the way that ants, many ants, will leave chemical pheromone trails that make paths between the nest and food sources that other ants can follow to help collect food. So we can do something like that, but we're not limited, the way ants are, to just sort of a trail of breadcrumbs. We can store additional information in the environment. And the fact is that humans use stigmergy all the time, very rarely under that name. But we're constantly leaving information in the environment to help influence future actions. And for instance, if you didn't know where the Asgard was, in this area you could tell where you were and how to get there based on the signs that say Mass Ave, and on the front of every building there's a sign that gives the number, that indicates the location of the place where you are. It's a case of storing location information in the environment in the location where it's important. So we can do something similar here. Let's suppose that every block that's part of the structure can have its coordinates written on it. Okay, so now when a robot comes to the structure, can figure out where it is by looking at the sign on the nearby block. And when it attaches a new block to the structure, it can write the new coordinates to that block. So it's building a shared coordinate system out of the blocks as it builds the structure. One way that you could implement that could be with writable RFID tags. These are simple passive circuits that can store kilobytes of information rewritably and indefinitely without a power source. They're robust, they're cheap enough that they can keep them away free on the tube. So this is a way that now you can solve this first problem. To deal with the second question of avoiding separate robots attaching inappropriately separated blocks in the same row or column, we're going to rely on the fact that they're all identically programmed. They're all obeying the same conventions. So for instance, everybody is circling the structure in the same direction. It's counterclockwise. So if robots following the perimeter will only ever start a new row of blocks when they get to the end of an existing row, and then add additional blocks sort of thereafter in this consistent direction, and that can be going on in different places around the structure and different rows at the same time. As long as all the robots are obeying this convention, things are going to work out like you want them to. They're not going to be taking mutually conflicting actions. They're never going to attach separate blocks in the same row. They're going to get the thing you ask for.
You assume they start at the same point in the structure?
Doesn't matter where they start. So the statement that they should only start new rows from the end is still a little bit high level. Here's a pictographic representation of a very low-level set of rules that you can give these robots. Okay, so the idea here is, let's say they with the shape map and the position labeling, they can tell which sites are supposed to be occupied or left empty. So as a robot follows the perimeter, if it comes to a site where it's about to turn a corner to the left, or about to enter a site that's supposed to be left empty, like in this case, then set a flag. Continue to follow the perimeter, and if you come to another such site, here where it's about to turn the corner to the left, and the flag is already set, then it's okay to go ahead and attach the block. If the shape map specifies there's supposed to be a block there. And similarly, if as it follows the perimeter, it comes to a place where it's about to turn the corner to the right, it's all right to attach the block there. And so this now is a really low-level set of rules that you can give to robots along with a shape map, or a description of the structure you want, and they will provably build you whatever thing it was that you asked them to build. So we're done. This is an example of a complete system. So let's talk for a minute about extended signature a little further. You can change how much capability you put into these blocks. So doing things a little bit differently, but using very similar ideas, you can build a structure, you can build a system that will work using completely inert blocks, basically just building a house out of bricks. You can go in the other direction and actually embed a processor in every block, right, and give them their own ability for computation, but the blocks communicate with physically attached neighbors. And as you move back and forth along this axis, you're sort of passing off responsibilities between the robots and the blocks. So in the case I described, the blocks are storing location information, and the robots are responsible for everything else. In this case, with inert blocks that can't store location information, the robots are responsible for everything, and in the other direction, the blocks can be responsible for everything except movement. And this case actually is exactly the same as the problem of programmed self-assembly that I talked about earlier. The blocks here are now exactly analogous to the tiles. And the robots that are moving around are doing the job that in the usual framework of self-assembly is done by thermal agitation, or whatever it is that's shaking up the tiles. So you can also do sort of more explicit trade-offs between these different approaches. Briefly, more capable blocks tend to be more expensive. Building with more capable blocks tends to be more robust to errors that may occur. So algorithmically, you're not going to get errors, but realistically, if you're building something with 1,000 or 10,000 very simple components, things are going to fail. And when that happens, it's easier to detect errors, easier to correct them, when you've got some help from the blocks identifying and pinpointing those errors. And in terms of performance, there are a number of ways in which the more complicated, the more capable blocks can lead to real benefits in performance. So for instance, the amount of time it takes to build a structure. The more capable blocks let a structure be built faster, consistently for structures of increasing size. You tend to be able to take better advantage of the parallelism of the swarm, again with more capable blocks. There are more things available for robots to do as the structure grows. And building with more capable blocks, robots tend to be able to, the system tends to be able to accommodate more robots before sort of crippling interference effects start to appear. Let me just emphasize in closing that in all of these cases, the algorithms are provably correct. They're going to give you the thing you asked for robustly to variations in things like the number of robots and the order and time of interactions. So that's the, I guess, kind of technical part. Let me now show you some movies of this happening in real life. The first robot is one that I built for my dissertation a couple of years ago. So this is a laptop driving an ER1 wheeled base with a gripper. There's a camera which is set up pointing downwards, so the robot has a little bit of visual input ahead of it and to its left, just what's on the ground. For self-aligning blocks, in this case I did that with magnets, so if the robot drops a block in about the right place, the magnets pull it into precise alignment. So let me show you a movie now. And because of PowerPoint, I have to run this over here. So this is, if you can hear me, this is an extremely sped up movie of, I guess, a one robot swarm. And this is 100 times real speed. So this one robot swarm is collecting blocks from this cache on which new blocks appear, as by magic. And it's using them to build a structure I asked it for, a 3x3 square. And this is being done with inert blocks. It's just sort of an overview to see the system in action.
What are the inputs to the system?
The input is, I want you to build a 3x3 square, and there's a marker, there's a starting point.
Question, is there a rectangularity to the tiles or anything, or is that all rectangular? Is there a rectangularity grid?
Only the one that is being built by assembling straight lines. And I mean, so the robot is only capable of moving in straight lines, which means it makes a lot of motions that look unnecessary.
It seems to have a preferred direction. Is that a compass or inertial? Or?
I mean, if you go forward, I can tell it to turn 90 degrees right, maybe it'll turn 80 degrees right, maybe it'll turn 100 degrees right. It's not very.
So it just keeps going.
This one. Yeah, I mean, this is programmed almost in a logo kind of way. 450 right now. So, let's see, I think. So I might be able to run this from here. If this doesn't work, I'll ask somebody to click on it, but let's see if this will work. So this is a slower movie now, using label blocks. So each of these white squares on top of the handle is an RFID tag, labeled with the block's coordinates. This yellow arm has an RFID reader on it. And this is what the robot's thinking. It's trying to build this gray structure. It doesn't know what blocks are already present. It knows that there must be, an initiation point, a marker. That happens to be this block. So the first job is for the robot to go and find a block. Go to the cache. It does that by visual reference to this line on the ground. The end of the line is a landmark that you use to say, okay, I found the block. Now it comes to the structure, and the first thing it's going to do is, seeing it with the camera, is to read off its position from the nearest RFID tag, and now it knows where it is. And as it continues to follow the perimeter using the camera, it can update its position as it sees these block boundaries. It can recognize when it sees blocks that it didn't previously know existed. And at some point, it's going to come to a site where there's supposed to be a block, and there isn't one, and these rules allow it to attach one. And at that point, it sort of maneuvers to get into the right position, to add the block, it drops in place, and writes its coordinates to it for future reference before being ready to head back and pick up another block to continue. Okay, so this is, so I've kind of been talking big about simple robots, right? But that's a laptop. This is running MATLAB. So the next robot I want to show you is one made of Legos. This is work by a couple of Harvard undergraduates I work with, who essentially duplicated this system using Lego Mindstorms. So here's a Lego robot doing the same thing you just saw. And one nice thing about Legos, so number one, they're toys, right? They emphasize the fact that very simple robots can do this, but also they're inexpensive and they're replicable. So once you've got a one robot swarm, you can build another robot. Now this is a two robot swarm, which is enormously better than a one robot swarm because now they're not dealing with a static environment. The robots have to deal with each other. And the senior project of Crystal Scholl, one of the students, was to build these bump sensors that really let the robots act in each other's presence. For two of them now to be able to be active at once and to back off as necessary when they encounter each other, either around the perimeter of the space or around the structure in progress. The one in behind will back off and let the one in front continue. So great. It's a physical system doing what it needs to do. Good. Okay. So let me wrap up then by talking about if this kind of system were only ever capable of building two-dimensional structures out of one kind of material, there would be limited practical utility. So it's important to, if this is actually going to be usable for construction, to be able to build things, for instance, in 3 dimensions. So the biggest physical challenge in moving in 3 dimensions is dealing with gravity. And now, fortunately, if you remember at the beginning of the talk, I was arguing that some of the most promising situations for these systems were in settings like outer space and underwater, where you don't really have to deal with gravity, and then the challenge is algorithmic. You had a question?
So besides building the hardware and making the hardware work properly, what are the difference between simulations or models of action and is there a big difference?
The difference is it's proof of concept. You can talk about robotics, but until you've actually built a robot, people who work on robots are not going to believe that anything you've shown is real. That was the explicit purpose of building the robot. Yep.
You said early on that it was desirable to have some communication going along as possible between the individual members of the school.
I believe so.
Why is that?
So here's a couple of reasons.
One, bumping into each other.
Well, bumping into each other is, it's not the kind of communication where they're sort of, Agent A is trying to get a message to Agent B specifically. It's more a reactive thing. It's communication more in the sense of, it's not that A is sending B a message, it's certainly not an active message. It's, it's responding to its observation of the other's presence. And certainly the robots are responding to their own observations all the time.
So state merging communications and sort of beaconing to no positioning, that's not what you meant when you talked about.
I didn't read that, but I'm sorry.
State merging communication and beaconing, in other words, not bump into each other, those were what you meant by communication.
Right, so the state merging was implicit communication. And another way to avoid collisions might be actually sending out an active signal and avoiding each other. That's not a kind of communication that tends to have the problems of wireless networking. So less of an issue in terms of it being something that's not necessarily straightforward. It's not that it's not straightforward. It's not that it's completely straightforward to implement the bump sensors as opposed to an undergraduate senior project, but it's more to do. Okay, so 3 dimensions. So there's an algorithmic challenge of extending to 3 dimensions, and it's tricky, but it can be done. And so here's a simulation of this. I have not built in real life. Simulation of a swarm of robots that give them a picture of a 3-dimensional structure, and they're going out and again, same idea, taking actions as appropriate as they encounter them that will result in the thing that I asked them for. So one thing you notice here is that there's 2 different kinds of blocks. There's gray and there's black ones. And that's important, again, for real construction projects because real structures are not built of a single kind of material. They're built out of wood and out of pipes and out of sheet metal and all kinds of different things. So the approach I've described is not going to extend very readily to building the way things are built now. It's not going to work to install plumbing, for instance. But you may be able to. So again, let's go back and think about improving the system by improving the building material. So if instead of building with very low-level building materials like wood and plaster and so on, if instead you prefabricate higher-level building units, sort of sections of wall that already include things like electrical wiring and so on, and then when you join 2 of these up, part of the task is to connect these sections of grid. Or even at a higher level, maybe you think about building entire rooms, or in the context of a space station, sort of like a living pod or a laboratory pod or whatever, and those are the things that need to be assembled on site. And that, again, is an approach that is being taken right now in terrestrial construction in places like Japan and London. There are people who are prefabricating entire rooms in a factory, shipping them out to the construction site, and then assembling them there into apartment buildings that are not only showing all kinds of savings in terms of cost and construction time, but also winning major awards for design and livability. So again, this is something that can be done, it is being done, it works. So now, the approach I've been talking about extends very naturally to building with different blocks all the same shape, but different types. So you can, you have the choice of completely specifying in the shape map what type of block every block in the structure needs to be. That lets you build sort of pre-patterned, completely blueprinted structures. So okay, speed this up a bit. Okay, this might not be clear. That's supposed to be the gray thing logo. I guess that's not as picturesque as some of them.
Cool.
Sorry, I had to point that out. Okay. So, but it might be that you don't actually care about sort of the very fine details of what the final structure ends up looking like. You might care only about sort of functional relationships between different block types, and sort of putting one down here might constrain what you can put nearby. But beyond that, but that's all you care about. So that you might be able to provide those kinds of constraints, and then build structures that are different every time, that satisfy some set of functional constraints, but aren't completely pre-specified. And that's closer to what insects are actually doing, right? Termites are not building the same mound every time. They're building something that works for the situation that they find themselves in. You can actually take a step further in that direction and look at structures whose shape is affected or even determined by the environment they're in. So something I've looked at is using actually a somewhat different set of building rules. Let's suppose that you've got like a toxic waste spill that you want to build a protective barrier around, but you don't know in advance what the spill looks like. So you can send robots out with instructions to build a wall of a given thickness, and they will go out and build something whose shape is determined by the environment. Okay, so let me. This is good. Yeah, I'll say just a few words about some directions I think would be really interesting to take this kind of work in the future. So I think there's certainly more to be done in the area of extending this approach to larger classes of structures and so on in fabrication, for collective construction, as I've been focusing on for program self-assembly. There's more that can be done developing these tools for coordinating swarms. I've been talking about extended sig merging. This idea more broadly of storing location information in the environment is a very powerful one. It's useful in all kinds of contexts beyond construction. For instance, the use of RFID tags like this has been used in simultaneous localization and mapping applications. It's a big area of research in robotics, where storing location information in the environment is very useful in helping to make a map of that environment. Moving over to a different biological and bio-inspired system, morphogenesis is another area that's probably a similar flavor of biological shape formation, starting with a single cell that robustly grows into an organism of a given shape. And certainly that's known to be a system where location information stored in the environment is integral to its function. But I think it would be interesting to take that also in the direction of synthetic biology, which so far has been all about programming sort of, I guess, unicellular organisms to behave in certain ways or to show certain behaviors. So far, people haven't extended that to multicellular organisms, but I think one day, not very soon, but I think in the foreseeable future, we're going to be seeing synthetic biology extending to that, with the goal of being able to program a seed to grow into whatever thing you want to grow into. And let me just close with a real sort of science fiction scenario. So there's a standard science fiction idea that in the future we're all going to have microscopic robots swimming around inside us, clearing out our arteries and so on. Since we have those robots, what else can we do with them? So at the Harvard Institute for Biologically Inspired Engineering, we've been saying, wouldn't it be great if you could use that for implanting surgical devices? Let's say you want to implant a stent in somebody's heart, but you don't want to actually cut them open and have to deal with them being sewn back up and healing. It would be much less invasive if you could send in a bunch of robots with building material, or just to send in self-assembling building material, so that it assembles into the structure you want on site, and no invasive intervention is needed. Okay, so that's not going to happen in the next 5 years, but it might happen in our lifetimes. And so I guess on that kind of futuristic note, let me close and take questions. Yeah.
I was.
Oh.
Go ahead.
So what are some physical limits on the robots you can have and the size of the devices you can make using the machines to some kind of calculations on how strong the materials that we could are versus possibly?
You're asking very important questions of the wrong person. So, I'm not a materials guy, I'm an algorithms guy. So I don't know how to build any of these things, and I'm not, I can't state with authority what kinds of things can be done with existing materials. My goal is not so much to create nanorobots as it is to tell you what to do with them.
You looked at any of these things on sort of a multi-scale approach of building components with one set of agents and then building larger structures with others out of those components?
That's an interesting question. The closest I think I can say that I've come is specifying certain structures as in a kind of hierarchical way. So maybe you're trying to build a house that's composed of some number of wings, and each wing is composed of some number of rooms, and the room has sections, that sort of thing. But in that case, of course, you're still building all of them in space, and they're not moving once you've built them. So it's not really getting at the question you're asking. It's an interesting question to think about.
I was wondering about the failure model. What do you do if a robot dies walking?
So if a robot, so you realize if a robot dies out away from the middle of nowhere, it just makes no difference.
Right. It's blocking the path in
right.
part of the structure.
Yeah. Well, actually, every part of the structure is a critical part of the structure because you have to follow the perimeter.
Or it's holding the last part.
That's an interesting question. I don't tend to think about things like if you have 10,000 robots and 9,999